Next up, we have the Lita team presenting a workshop on their zkVM design. So we have Hadass, Dan, Morgan, and Mammy joining us. I will hand them the stage after this intro video.
Hi, everybody. So yeah, I'll be presenting a little bit about our prover design here at Lita. Next slide. Okay, so when we're creating a zkVM, there's certain criteria that we care about. First, on the cryptography side is correctness and security, which ensures that our zkVM satisfies the notions of security that make it meaningful. So we want completeness, soundness, and zero knowledge. Then something that's somewhat separate from security, trust assumption. So what are we actually proving it secure against? What context are we proving our security within? And then, of course, we have our efficiency measurements, such as speed and succinctness. We want our prover to run fast, and we want it to be as small as possible. Next slide. Okay, so the main technique we use revolves around IOPs, and sorry, that first bullet point isn't exactly correct. It's not. There's two types of IOPs. One is it could be a polynomial IOP or a regular IOP. In a polynomial IOP, the prover sends polynomials. In regular IOPs, they send just generic vectors. So basically, what we do is we start with sort of like a magical protocol where the prover is sending an oracle to a polynomial, and a verifier is able to open that polynomial at any point it wants. And using this sort of magical scenario, we're able to sort of neatly prove the properties of the zero knowledge proofs we want. Then we compile it using a different type of IOP where the prover sends vectors instead of polynomials. So the polynomial oracles are instantiated with IOPs, which in turn are instantiated with hash-based non-interactive polynomial commitment schemes. So that's basically the pipeline of how our proofs are compiled. And there are a few types, depending on what type of polynomial you're using: univariate, multilinear. Currently, we use univariate, but we may be switching to multilinear soon. The key difference is that in univariate polynomials, you end up needing to do the proof with polynomial quotients, whereas in multilinear PCS, you can avoid that. So it ends up being more efficient in certain settings. And that will be something we might do down the line. Okay, next slide. So there's different considerations for polynomial commitment schemes. First of all, what ring is the coefficient over? Currently, we use the baby bear field, which is very efficient, but there's other alternatives which might be a little more efficient. A really cool thing would be to make this work over rings that are like, like standard computer architecture, like ZMOD 2 to the 64, but that's still an open question how to do. And then, as I said, univariate versus multilinear, singular versus batch. Batch PCS is a way to make, we do use batch PCS to make things more efficient. And then elliptic curve via hash-based ones. I'll discuss this a little more later, but hash-based ends up having faster prover time, so that's the one we use, even though they have slightly larger proofs than elliptic curve ones. Okay, next slide. All right, so here's a table of different types of PCS. So KZG is sort of the original concretely instantiated PCS. It has a linear time prover. However, that linear time prover has a lot of overhead. So concretely, it's still slower than the non-linear time prover ones we use. However, it does have very small size commitments and verification time. Other cons, though, besides the high prover complexity, is a public key assumption, linear size key, and it's not post-quantum. Then we have inner product argument, PCS, which have transparent setup and a linear time prover, but have still high proving complexity. Next, we move to univariate Fry-based, which is currently what we use, and that has a really concretely inefficient prover, even though it is quasi-linear instead of linear. But it also is post-quantum and has a transparent setup. The proof sizes are larger than with KZG and elliptic curve based ones, but it's a manageable size, I think. Although improvements on that will be exciting. Multilinear Fry, for example, basefold has the same complexity as univariate Fry and same complexity as univariate. Basically, the pros and cons that are listed here are the same, except it's multilinear, which, as I described earlier, is more efficient than univariate. So you can get a speed up by using multilinear Fry over univariate Fry. And finally, there's interleaved code-based ones, such as Breakdown and Ligero, which are super fast. Due to two reasons: one, the interleaving technique, and two, the speed of the code. However, the trade-off there is a larger proof, so those are used more rarely in practice. Thank you. That's the end of my section.
Hello. Hi, I'm Tesseract. You can call me Tess. I'm also Dan sometimes. And I'm going to be talking about optimizations and how to design an efficient VM based on Plonky 3. So there's generally three properties to optimize for in ZK and VMs in particular. One is succinctness, which is having a small proof. One is speed, which is the amount of time it takes to produce a proof. And one is efficiency, which is the amount of computer time it takes to produce a proof. The difference being that efficiency talks about the total number of cycles needed to compute something. So if you have something that's massively parallelizable, which is often the goal, then you might have very good speed. It takes a short time to produce a proof, but it takes a lot of resources to do so. You need to use a lot of cores. So these things often have some amount of tension with one another, especially succinctness versus the others. So the fastest provers, as Hadas mentioned, are generally based on hash functions, whereas they tend to produce large proofs compared to, for example, proofs based on elliptic curves. However, you can kind of have your cake and eat it too sometimes by proving in multiple stages. So this is the ultimate game plan for Lita, that we start with this hash-based proof, which ends up being large, but then it's still a lot smaller than the original computation. The factor is log squared of the original computation size. So then we can take that and prove that inside of a smaller zero-knowledge system. So it's a much smaller circuit than we start with. We can get away with a somewhat slower prover, and that lets us get the proof size down to as small as possible. So this is a pretty standard trick where people will use something like Plonky 3 for the original proof step, and then fall back to even something like Groth 16 or Plonk in order to get a very small proof that you can put on chain. This is more or less a requirement to use ZK on Ethereum because of the high verification costs on chain, but is generally desirable for many use cases outside of that as well. Next slide, Morgan. So a major question and this has been really important for Lita, is to talk about whether the instruction set should be optimized for ZK or not. So we kind of fall on the other side of this question from most of the other teams working on ZK VMs, in that many of the others are using something like RISC-V as their instruction set. The benefit of doing so is that RISC-V has existed for a long time. Rust-C out of the box compiles to it. You can use tons of off-the-shelf tooling for security, for auditing, for compiling. However, RISC-V is not optimized for zero knowledge. And that means that it's a little overly complex relative to the simplest set of instructions that you could imagine using to encode your computations. For example, in regular computers, it doesn't really cost much to branch. In hardware, you can have speculative execution, things like that, that really cut down the cost of branching, whereas in ZK, you really pay out the nose every time you branch. You basically have to follow all branches of every conditional. So this means that reducing the number of opcodes and having each one do a little bit more can be advantageous. Another major architectural decision that came into play for us here is the elimination of registers from our system. So all memory is main memory. We have a stack and a heap, but both are allocated in main memory. The only piece of data that we need to track as a register is where the frame stops, or where the stack stops and where the heap begins. And that's called the frame pointer. That and the program counter, which is which instruction we're about to execute, are the only two running registers for Lita. So this helps us save down a lot of conditional logic based on, is this a register form of an operation or a memory form? And it also, there's no point to having registers in the ZK setting because we're not moving electrons around at the speed of light between various types of caches of memory. We're doing polynomials, so there's no notion of locality in the same sense. I think that's all I wanted to say on this slide. And then, yeah, this is the second major point I want to make about Lita, and these are really the two things that I think are the most core to our design philosophy. Lita is a modular zkVM. So this is a design pattern that has really become more popular, I would say, in the last few years, especially as technology around things like lookups have improved. But if you look at the first zkVMs out there, I'm thinking of something like Miden, maybe Cairo, as of some years ago. You have one really big circuit, and that circuit does everything. It does, all 35 opcodes. And this is inefficient. As I mentioned in the last slide, that means that you're kind of paying for each of those computations every time. So being able to split up your trace into multiple traces allows you to have some of this conditional a la carte cost profile where you only pay to execute the instructions you actually execute. So how this looks for us is that our main circuit, the circuit that produces the CPU, that increments the program counter, decodes instructions, is as small as possible, and we have separate circuits to compute each opcode, or maybe collection of a couple related opcodes. So there's one for addition, there's one for division, there's one for shifts. There's also outside of the arithmetic ones, there's one for checking the program ROM, there's one for memory. And by separating each of these pieces of the argument, you're able to really cut down on the amount of waste that you have of columns that are sitting around not doing anything for instructions that aren't relevant for them. This also helps for the very important question of adding precompiles to the system. So our system is particularly oriented around the idea of extensibility, where we have this set of chips and our machine doesn't have the set of chips baked in at a very deep level. So if you want to add, for example, a computation of your favorite specialized hash function for your niche purpose, maybe no one else has built that one, then we want to make it so you can do this yourself without needing to be an expert in our code base. So for both efficiency reasons and extensibility reasons, we really prefer modular. How am I on time? I know someone was giving me a time warning, but this was the last main thing I wanted to say, but I think I have one more slide. And so this all is the way that we make these decisions in the math setting of snark circuits is, right, we need to turn this sort of abstract description of a computer into something that our ZK can understand, which means a set of polynomial equations. This is a universal thing in all types of ZK. The way that we decide to do it is using the AIR, algebraic intermediate representation constraint system. This is historically associated with Starks, although, and Plunky 3 is a Stark, although there's no real intrinsic relationship between this particular constraint system and Starks themselves. However, this constraint system is really well optimized for zkVMs in particular. So a zkVM circuit, why this system works well is a zkVM circuit is executing the same thing over and over again. And the computation in each step is relatively small compared to the whole thing. So AIR, the constraint system, says that for every row and for every subsequent row of your trace, a particular equation holds that relates the values on the two rows. So this works great for repetitive computation like a VM. This doesn't work as well for maybe something really specialized that doesn't have this structure. So it was a big deal in 2018, 2019 when the Plonkish constraint system came out and showed us how to use something very similar to AIR that allows for less structured computations. And at the other end of the spectrum is R1CS, which is mostly used, I think, in academic papers and some elliptic curve systems these days, as well as specialized circuits outside of the VM context. And here you have no notion of time or anything like that in your constraint system. You have your whole trace is one big vector, and you make a bunch of claims about equations that hold on this vector. This has some advantages in other contexts, but is generally not what you want for a VM, and most teams do not use this. And then the final question is, all of this, when talking about polynomials, there's a field. So the field is where the coefficients of the polynomial are, it's where the evaluations are, and it's where the challenges are. These fields can be extensions of one another. All of those three don't need to be the same. And this is something that's been a big headline this year, is that it's due to the existence of circle Starks, an exciting new research idea. I won't say anything about that more, but due to the existence of this, it's unlocked the ability to use certain fields called Mersenne prime fields, where field operations are really efficient to do in hardware. So this has enabled a pretty solid speed boost, maybe 50%, 25%, something like that, on existing Stark systems, essentially entirely by switching out the field. It used to be the case that everybody used really large fields, which is necessary in the elliptic curve context. You need a large prime. But in the Stark context, you can use smaller fields and pass to an extension to get challenges. And that's where you get the cryptographic, 100 bits, 128 bits of security, even though you're working in a 30-bit field. There's even been a couple years ago, some exciting results pointing to how to use even smaller fields than the 30-ish bit fields that we use today, which are aligned to the 32-bit word size of computers and our ISAs, but also have to be large enough to hold the entire trace. So the field needs to be at least as big as the number of rows of the trace. But there's this result, Binius, that shows us how to get away from this too, enabling you to work in a field that's sort of as small as you'd like, so big enough to make the computations you'd like to make in. This requires stepping away a little bit more from the standard Stark proof system than we've done so far, but this is an exciting direction we might explore in the future. Okay, now I'm actually done.
Hi, mic check. So I'm Morgan Thomas. I'm a crypto engineer at Lita. I'm going to talk with you a bit about compiler design as it relates to zero-knowledge virtual machines. So we've got some interacting considerations here when we're trying to prove executions of programs, such as like, what programming language are we going to write it in? Whatever language that is, we need to be able to compile it to run on the zero-knowledge virtual machine, and that's going to have some instruction set architecture, right? The language that it knows how to interpret. So that implies you need a compiler to the instruction set architecture from the source language, unless you're going to like write directly in what the zkVM can interpret. Okay. And also, like, so the design of this instruction set architecture for this VM is going to depend on the choice of proof system and arithmetization. And so, like, ultimately, all of these things have interacting considerations. Like a choice in one of these squares affects potentially all of the others. You know, so also, like, we should throw in here, right, the problem you're trying to solve, because the problem you're trying to solve is going to affect, like, what kind of instruction set architecture would allow you to most efficiently implement a solution. And so that's where, like, the modular architecture for the VM comes in. You can have ISA extensions, which allow you to solve specific problems that are peculiar to your application more efficiently than you could with general purpose instructions. And if you want a modular zkVM like that, that in turn is going to affect the design of the compiler and the implementation of it, because it's going to need to support all of those extensions and, like, usefully, like, emit them when presented with certain source programs. Okay, so let's, like, drill down a bit into the choice of instruction set architecture. So what exactly are the choices involved in this? So we've got the memory model. So like most, like, modern CPUs have, like, what's called a von Neumann architecture, where they just have a single address space where both code and data live. And this address space is readable and writable and executable. So you can jump to it, you can load to it, you can store to it. Not all computers have always worked that way. Like, the first computers, as far as I understand, were a Harvard architecture, where you have a separate address space for the program and the data. So the data address space is readable and writable, but not executable. You can't jump to it. And the program address space is not readable or writable, but you can jump to it. Like, so, and then, you know, with a Harvard architecture, you may also want, like a program ROM address space. This would be a variant on the Harvard architecture, right? But sometimes you want, like, the program to consist of both code and data, like it has some tables of constants or whatever. And so in some cases, those might be in a third address space. Which is kind of the case with Valida, but then there's only two address spaces that are accessible to the program. Like, the program ROM just gets loaded into the RAM at program startup. So Valida is more of a Harvard architecture. Now with and then, you know, there's questions like, how big are these address spaces, which affects what is the size of a word. You know, is it 32 bits? Is it 64 bits? So that's the memory model. And then we've got the instruction set, like, essentially what operations can you do, what kind of flow control operations are there. You know, you probably want, like, some conditional jumps and some unconditional jumps, and you want basic arithmetic and logical operations probably, and you want like, instructions for reading and writing memory, instructions for any IO interactions that are possible within your platform. So that all goes into the instruction set. And then, you know, registers. So registers are a concept in hardware design where you have a piece of memory that is very close to the arithmetic logic unit of the CPU. And it holds a small amount of data as working memory. So, like, typically a register might be 1 word or maybe 4 words or something like that. And opcodes, like, for arithmetic and logic, can act directly on registers, right? So Tess was alluding to why registers exist in hardware designs. It's because of locality considerations. In a chip or in a physical system, information moves no faster than the speed of light. And so by having the location for, getting the inputs and storing the result physically close to the arithmetic logic unit, it is faster to access. So that like leads to the concept of general purpose registers. But then, and that's what they are essentially, is registers that you can do these things to, right? Like arithmetic and logic. And there's also special purpose registers, which serve a special purpose, like such as they hold the program counter, i.e. the address of the next instruction to execute, or the one that's currently executing, right? Or they hold a pointer to the top of the stack or something like that. So like in Valida, the concept of general purpose registers doesn't apply, but special purpose registers are there. Yeah, calling convention, like how does a function call another function? How do they pass their arguments? How do they pass their return values? Yeah, that's key questions and ISA addresses. Now, like those questions of how you design an ISA, they interact with, how do you design the zkVM? How do you design the proving system? You need to pick a field size for the proving system, and that's going to affect the efficiency of that proving system, but it's also going to interact with the choice of word size for the ISA. If you have a smaller word size, then programs may need to emit more instructions to get a job done because they're working on smaller pieces of data at a time. But you then need like less field elements to represent a word with a smaller word size, depending on the field size, unless the field size is bigger than the word size. So like in Valida, we're using like a small field size, less than 32 bits, and we have a 32-bit virtual machine. And we represent words generally with byte decomposition, splitting them up into 4 8-bit values. We're looking at maybe splitting them up into 16-bit words, at least for some purposes. That could be better. Anyway, I just want to like talk a bit about why we've been going into all of these compiler engineering efforts at Lita. As Tess alluded to, when you're using a general purpose ISA such as RISC-V or ARM, you don't have the need to create a new compiler backend that generates code for that. Whereas we do have that need because we're working with a novel ISA, Valida. And so like our contention is that we get significant wins in terms of proving speed and proving efficiency by using this custom ISA, because some of the choices that we made, e.g. the choice not to have general purpose registers, they work great for a zkVM setting and they wouldn't work well for a hardware setting. And so these general purpose ISAs, they are originally designed to be implemented in hardware. So they will inevitably be optimized for that use case. Whereas Valida, being designed natively for a ZK proving environment is optimized for that use case. And this slide sort of goes a bit more into that. That's that. And I'm just going to go right into this last talk where I'm filling in for Mammy, who's not able to make it today. This is about zkVM hardware co-design. So what are we talking about? So the goal of this process is to select a prover, a zkVM, ISA, all of that, right? And a hardware platform to run the prover on, such that we optimize for the time it takes to prove an execution and the energy it takes, and the cost of the hardware that runs that prover. So 2 different approaches we can take. We can run on CPUs or GPUs or FPGAs, or maybe in the future we can run on cryptographic coprocessors, and I'll go into each of these a bit more. So starting with CPUs, these are the central processing units. So they're designed to be like as versatile as possible. They're very good at executing complex logic with a lot of branching. Recent CPUs also have some ability to work with vectors. They have like SIMD, single instruction, multiple data opcodes in them, and you can use those to deal with some small vectors. And so that's helpful when working with cryptography. And CPUs like have the most mature development tooling for them. You know, this is like the starting point of computer science and compiler technology. And so everyone knows how to program CPUs who knows how to program. Big downside of CPUs is like because of their generality, they are not as energy efficient as the alternatives we're going to look at for repetitive numerical algorithms, such as the ones that are the primary cost centers in zero-knowledge proving. That's CPUs. Now GPUs. These are modern general-purpose GPUs. Are essentially machines for doing linear algebra. They are good at working with vectors and matrices. They have like SIMD like CPUs do, but they take it to a whole different level. And the tooling for programming with GPUs is pretty mature as well. It's not as mature and well understood as the tooling for CPUs, but it is better in that respect than the other things further down this list, I think. The major like failing or shortcoming of GPUs relative to CPUs is they're less effective at really complex branching logic. When you have to do like different things on each element of a list, then using a GPU may not turn out to be a win. So there are some parts of the proving process, particularly things like generating polynomial commitments and opening proofs, those things are amenable to vectorization. They're more easily done on a GPU. And then other parts of the proving process, particularly execution of the program, generating a trace is probably more effectively done on a CPU. Yeah, I'm gonna wrap up here in a couple minutes. So with the FPGAs, they are they're field programmable gate arrays, and so you can program your specific algorithm into the circuitry, and you can get even more energy efficiency than you get with GPUs, but they're more difficult to program, and it might be harder to do complex logic in them. So that's FPGAs. And then the cryptographic coprocessor, this is like sort of emerging technology. Fabric cryptography has been working on one for over a year now. And this is a lot like a GPU, except it's optimized for working with finite fields. So this would be a big win for doing cryptographic computations. I think we would see substantially better energy efficiency and latency than we get with GPUs. Downsides of this is very, very expensive to develop, and currently it's not on the market. So some additional things to think about when picking out the hardware and the prover, right? You want to think about what operations are efficient on the hardware and try to make your prover be based around those. If you're going to run the prover distributed across multiple chips, then you need to think about the communication bandwidth and latency between those chips. And if you're running it across a network of computers, then you have the same issue but dialed up further. And so those are things to think about. That's it. Thank you for your time. Hope this was helpful.